In this video, we're going to look at another example of the alternating series and the remainder in the alternating series. So, for this example, we're looking at the function e to the negative 1 minus 1. And I'm going to call it a function specifically because, well, we can use e to the x minus 1. And then that x can be replaced with what we need it to be replaced with. In this particular case, e to the negative 1 minus 1 actually equals to this infinite series. Okay? Again, in future videos, we'll see how this can play out and how we can actually prove that this thing is equal to what it is. But for right now, let's just trust that it is. So this thing is equal to this infinite series. The question is again, how can I ensure that the approximation of this value right here is accurate within, in this case, again, 6 decimal places, so 10 to the negative 6 one more time. This is what we want to prove to be the case. But now it's important to understand that, again, one more time, this is an alternating series. Number one, this is a little bit tricky to do. We have to prove that 1 over k factorial is always non-increasing. Well, it's not something we can prove. It's actually something that the way that the absolute value, sorry, not the absolute value, the factorial is defined. Given that k will always be increasing, the factorial will simply multiply all the values together. It means that we're going to go ahead and do 1 divided by a number multiplied by a larger number than itself over and over and over again until we get all of the possible numbers, and this bottom piece is always just simply going to be increasing. So since this is always increasing, this overall thing is always decreasing in terms of its value. So we can argue then that this thing is always non-increasing as a whole. And again, this more of a logic statement because we can't really take the derivative of a factorial. So in some cases, we're going to have to make those stipulations. Number two, we take the limit of this, the limit as k goes to infinity, and again, taking the limit of a factorial is a little bit difficult, but again, it's logical that this top piece is a constant and the bottom piece is increasing without bound, so this thing ends up going to 0 as a whole. So we did prove that this thing is actually an alternating series and therefore converges, and again, in this case, I know that this particular series converges to this particular value. So the question is how many terms do I need in this alternating series to make sure that the remainder is less than 10 to the 6th? Now, why do I go through all of these steps? Well, I go through all these steps because I need to understand that a sub n is equal to 1 over n factorial, again, ignoring the negative 1 to the power of k. And therefore, a sub n plus 1 is equal to 1 over n plus 1, in parentheses, factorial. And I know for a fact that r sub n by theorem is less than or equal to a sub n, and a sub n is equal to 1 over n plus 1, sorry, a sub n plus 1 factorial. Again, the alternating remainder is always smaller than its first neglected term, the first term that we don't use in the partial sum. So if I know that this is true, and if I make r sub n then therefore less than that, I know that to be true, I know that to be true, I force this to be true, I can guarantee then that r sub n is less than this value. So again, this is the thing I'm trying to end up concluding or proving. And the way that this works is I'm going to actually go through this a similar way that I did the other one, but the problem is that when I do this, n plus 1 factorial is less than or equal to 1 over 10 to the 6th. Sorry, that's 1 over 10 to the 6th, not a positive. Sorry, not a negative, that's a positive. I'm going to go ahead and multiply both sides by n plus 1 factorial as well as 10 to the 6th, giving me 10 to the 6th is less than or equal to n plus 1 factorial. Now, I can't solve a factorial. There's no mathematical process to getting the factorial away. I don't know what the inverse of a factorial is, like a square root, square rooting a square root, or taking the natural log of an exponential, or taking the inverse sine of a sine function. There's no inverse function for factorial. So there's no nice way to solve this other than, and wait for it, guess and check. So you're going to start by plugging numbers into this n value. So if n equals 1, what do I get? If n equals 2, what do I get? If n equals 3, what do I get? And we're going to go down a list of options to try. Now, once I get to n equals 8, that's going to provide me with 8 plus 1 factorial, which is 9 factorial, which is really something like 2,880, but that's actually less than 10 to the 6th. So we're not yet there. If I try n equals 9, I end up with 9 plus 1 factorial, which is actually 10 factorial, which is equal to 3,628,000, I think 800 is what the actual value ends up being. And it's important to understand that that is greater than 10 to the 6th. So we're looking for n plus 1 factorial to be greater than n to the sixth by plugging all these values in. If I plug in n equals 10, well, yeah, that's going to work too because the previous one worked. So it's not that we have to find a value that works. We have to find the value that is the smallest value because, again, we don't want to add up an infinite number of terms. Well, there's obviously a term that we can pick that's, say, 10,000 in this case that will work. In the previous example, it didn't work out that way. There was one specific value that we had to pick such that it was going to be then greater than what we were looking for, or smaller than, in this case, what we're looking for. In this case, I want the smallest possible number that will satisfy this inequality. So I'm, again, just simply checking values. Now, if we start with 1, 2, and 3, we don't really want to work with those numbers if it obviously doesn't seem like it's going to work. We can jump to, say, 12 or 20 or whatever, and then notice that those work and continue to work our way back down, or pigeonhole the problem where we start at 20, doesn't work, or 20 is too large, it works. We then jump down to 10, we realize 10 works, we drop down to 5, we realize 5 doesn't work, and we start pigeonholing back up until we get to the value of 8, which is the first value or the last value that doesn't work, and 9 is the first value that does. So if n equals 9, if we add up the first 9 terms of this series, we will conclude that it is accurate to this value, specifically within 6 decimal places, which, again, in the previous example, we had to have almost 900,000. In this one, we really just need 9. 9 terms is actually really nice to add. So we can argue that this series converges to this value quite rapidly in the whole process of this problem.